this class so that I can finish one topic and we can wrap up transformations for good, and we can go to actually describing manipulators when we go on to the next class. Okay, so you just reviewed R3 by 3. The R3 by 3 transform only takes into consideration rotations, okay? And as we mentioned when we talk about frames, there are two types of things you can do. You can do a rotation and you can do a translation. Right? A translation is a linear displacement of a frame. This is an angular displacement, right? So when you have a translation, you can translate only about the given axis. So for example, I can translate this, if this is my x, y, let's say my z is along the line perpendicular to the board, I can translate a frame along these axes. So if I move the frame here, if this is my frame F0, I want to move the origin here to F1, then this would be my new frame, right? By a displacement of A. Okay? So let's call this as Y1, X1 would be here, and Z1 obviously would be here, right? And same thing will happen when I try to displace it in either direction by negative A minus along Y, that's called the displacement B, and so on. So to encompass this within a singular matrix is one matrix that can have both rotation and translation, we have to go to a 4x4 format, which is known as a homogeneous transform. A 4x4 transform, which is a homogeneous transform, we write a homogeneous transform as follows. R 3 by 3, 0, D 1. Okay? What it means is you have your rotation defined here, your frame rotation defined here. This is your rotation. And any translation that happens is also defined here. You have a frame rotation and frame translation encompassed together. So for example, R3 by 3 will be like this, R11, R12, R13, zero, zero, zero. This is 0. D will be X, Y, Z, whatever translation you have, and 1. So this is your rotation matrix. This is your R3 by 3. And this is your D. Any displacement or any translation. Alright? Now, this matrix, we call it as a homogeneous transform. Homogeneous transform is because it reflects both the rotation and the translation. So for example, I only have a translation. Let's say I do not have a rotation. I only have a translation. What happens to the, in the case of a zero rotation, what happens to the R3 by 3? What is R3 by 3 for a zero rotation? Zeros? No. Ones? No. Identity matrix. If any rotation about any axis is 0, either x, y, z, this becomes I 3 by 3, right? For a zero rotation. So if I want to do a homogeneous matrix H for a translation along x, then this will be the homogeneous matrix because there is no rotation, there is only a translation, right? Same way, you can have a translation. Let's write this as translate x. Same way, you can have translate y. And translate z. That's pretty straightforward. Obviously, in some cases, you can have both of them. So you'll have xy, or you can have xyz. It does not matter because you're multiplying identity matrices for the most part. This will only just add on to this. Okay. So when we do a problem, we'll get into this. Conversely, I can have a rotation matrix as a simple rotation as a homogeneous transform. So I can have rotate x. So this will be by, let's say, theta, right? So in the homogeneous form, obviously, it's going to be okay. So this is again the same matrix that we have previously. Rotate y. Right? And finally rotate z. So you have to, basically this is a nested 3 by 3 matrix, but I'm just writing this to explain the point here. Okay. Now if you remember the properties of R3 by 3, which is an orthogonal matrix, H4 by 4 is not orthogonal. Okay. H4 by 4 is not orthogonal. Okay. So the idea that just as R inverse, R3 by 3 inverse was equal to its transpose does not hold true for R4 by 4. R4 by 4 is, H4 by 4 is not equal to H4 by 4 transpose. Okay, this does not hold true because this is not an orthogonal matrix. Why is it not orthogonal? Because let's say I have a displacement here of 1. Then this row does not, the magnitude of this does not remain 1, of this column does not remain 1, so it's not a unit vector anymore. So this you will not find that these matrices are not orthogonal. So if you want to do a inverse of H, the inverse of H, let's say you write H as following. If H4 by 4 is R D 0, 1, then H inverse will be equal to R transpose 0 minus R transpose D 1. Okay, where D is XYZ, D is XYZ, and this will be a multiplied product, so you'll get a 3 by 1 matrix. So this will be D is, let me write it here. Okay. So when you do an inverse in this case, you cannot take a transpose, but you'll have to take the transpose, multiply with D, and do it in parts and put together the inverse matrix, as opposed to just directly taking the transpose. Now, let's take an example where you have a transforming a point. Now, normally it's easy when you do a point. If a point is given like this, P is equal to, like you did in your example, quiz today, 1, 2, let's say that. It makes sense to multiply with a R3 by 3 matrix because now you have a 3 by 3 matrix and you multiply this with the point 0, 1, 2. Okay. So this is R 3 by 3. What happens when you try to multiply a 4 by 4 matrix? You have a H4 by 4 and the point is only 3, right? This is, you have 0, 1, 2. You can't multiply this. Okay? So what we do here is we introduce a value here which we call as the scaling factor. Okay. usually, for our case, for a scale of 1, that means it represents the exact value of the axis. If I have this, if I want to magnify this, then I'll go below 1, okay? Or if I want to minimize it, then I'll go above 1. That means this is a factor that is multiplied to this. For our purposes, we'll just keep it at unity. That means the scale is exact to the units. This is mostly used in your computer games or 3D software. When you scroll in your mouse, things expand or they shrink. That is just shrinking this scaling factor. So you can scale the vector to whatever units you want by just changing this number. This number is divided by this so that you can come up with a larger box or a larger vector in that particular direction. So this will keep it as 1. So now you can multiply these two matrices. So whenever you have a point given, you will add 1 to it so you can multiply with a 4x4 homogeneous transform. So let's do an example with setting up homogeneous transforms, and then we'll go ahead and
I'm a bit lost, I'm sorry.
Okay.
So what you erased, the P is equal to 0, 1, 2.
Okay.
And then what is the...
When you have a R3x3 matrix, right? It's okay to multiply with a point, which is 3x1, right? Which is P transpose. But if I have a 4x4 matrix here, H 4x4, I cannot multiply by a matrix that is 3x1. Right? Because you, in a point you only have, P is only X, Y, and Z. Alright? So we introduce A here, a number, which we call it as a scaling factor, and for our purposes, we'll keep the scale as 1. So now, this becomes P4x1, so that you can multiply the point. Is that clear?
Yeah.
Alright. So let's take an example where we have to set up.
Is it always 1?
It's always 1 for our case, okay? For the purposes of our case where we measure units, we do all the units given to us are to the scale, but if I want to say I want to scale this twice the size, right? Then this will become 0.5, half. That means all these numbers are larger. Okay. Let's take this example where we have to do a homogeneous transform. Set up a homogeneous transform for this case. Okay, so we have 3 frames here. The first frame is this. We have Z0, Y0, and X0 is into the board. X0 goes within the board. Here we have another frame. Actually, we have 3 frames. So this frame is X2. Y2 is upwards. And outside the board is Z2, perpendicular to the board. X1, X0 is within the board, Z2 is outside the board. Then we have another frame, which is X1, Z1, and going inwards is Y1. Okay. So this is 90. This angle is 45 degrees. This is 1 unit. This is root 2, obviously, and this is 1 unit. Okay. Now this is frame 0. This will be frame 2. This will be frame 1. We have to set up a homogeneous transform between the 3 frames. So we need to find what is. Let's start with doing a transformation from F0 to F1. Okay. So we want to do a transformation from F0 to F1. This is defined by H01. Okay. So let me draw this frame first. So we want to end up with this one, right? So our eventual frame should be this, which is X1, I'm sorry, Z1, this is X1, and this is Y1. We're starting with this frame, which is Y. X naught. So you want to go from here, F naught to F1. So what are the rotations needed to, okay, first thing is, when I move this axis, there are two ways you can do it. Just give me 1 second and then you can copy down. Either I can move the frame exactly like this, then translate it upwards, okay? So basically, this is X, Y, Z. I can turn them around like this and then move the frame upwards like this. Or I can move it upwards and then I can turn them around. So let's say that the first thing that I want to do is translate it. I want both the origins to coincide first and then we'll do the rotations. For both the origins to coincide, what is the displacement needed about which axis?
1 over the
Z0.
1 over the z-axis, right? So the first translation, for the first thing that you'll do, step 1 is translate along z by 1, okay? That is the first thing that we'll do, which is translating so that both the origins will coincide at this point, O1. Okay, let's call this as O0. Now let's say the origins have coincided. What we want to do is we want to align the axis. A single rotation, if there's a single rotation that would do it, it's perfect. But in this case, it will need more than one rotation. So what we'll do is, we'll start by aligning one axis first. So let's align Z. We'll have to drop Z like this to align it with Z1. So in this case, I'm rotating along X by an angle of 90 degrees. Okay? So when I rotated along X by 90 degrees, what I'm doing is, this is the positive direction of X. I'll drop it like this, and here you'll have X naught. Y naught will go like this because you have flipped the axis like that, and this will remain as it is. I'm sorry. Z. And this will be X naught. So what I have done here is, my first rotation here was rotate X by 90. Okay, so the second step here will be,
Professor, why is the X naught in between the Y naught and the Z naught?
I'm sorry,
Oh, it was about the X naught axis, that's why? The rotation. Because if it moved like that, wouldn't X also move with it? Or is it
if you're
about the
rotating
X
about an axis, that axis should remain constant.
Constant.
You can, if that moves, then your whole principle, you
Okay.
cannot rotate about a moving axis, right? The axis that you move about is fixed. I'm rotating about this axis.
Oh.
Okay? So when I do this, this will drop like this, right? So this is going to be okay. Now, what is the next? So Z is aligned. I cannot touch Z. Z is aligned. Otherwise, I'll be undoing what I did here. Z is fixed now. Now, to align Y to this and X to this, how do I need to rotate?
Along Z axis 90 degrees.
Along Z by 90 would be like this. That would bring Y outside the board.
Minus 90 degrees.
Negative.
In the opposite direction, in the negative direction. So this would be minus 90. Okay? So here you'll rotate Y negative 90. So here, now this will be Z naught as it is, X naught will go down, and Y naught will be within the board. So this perfectly aligns with that frame. So now you can write this as 3 as rotate about Y, sorry, Z. Z negative 90. Okay. So your H01 will be equal to, H01 will be equal to multiplying these matrices, which will be 0, 0, 0, 0, sorry, 1, because that's Okay, here we'll have cos. And we have z, so this will be cos minus 90. All right. So in this case, I'm just writing them as rotate x. Please do not confuse this with 3 by 3. These are all h4 by 4 meters. Okay. We have moved beyond doing 3 by 3. I'm going to erase this.
No.
Oh, no.
Professor,
Yes.
can we do the rotation and the translation at the same time?
It absolutely does not matter. So let's say that I did not do this. I do a translation later, right? So this translation matrix will come here, right? If I do it at the last, right? Because these are all, if you look at this, what type of rotations are these? Are these current frame or fixed frame? Current frame. You're always dealing with the current frame, right? So if I do the translation to the end, it will come here, right? Because this is an identity matrix, this will not change. Only thing that will change is you'll add 1 here, that's it. Okay? You can do exactly the same thing, do the rotation first. You can do the rotation and then do the translation. It absolutely does not matter. Okay? Because this is a complete identity matrix. The only thing that will happen when you do that is this will be exactly the same. Instead of getting 1 first, you'll get it at the end. This matrix will only change this part. It will not change any of this. Okay? So whether you do it here or you do it here, it makes no difference.
So these 3 are what we did up there, right? These 3 matrices.
First we translated so that you can move the frame upwards. You move the frame so that both the origins coincide.
Okay.
Then you rotate them so that they both,
And then we multiply the 3 of the.
because these are all current frame rotations, you'll multiply them consecutively. So this one, H01, will be what's the question?
I was wondering, like, do we have to do fixed rotation in this course? Like when we trans.
See, the idea is to make those 2 frames aligned, right? If you have to do this through a fixed rotation, that's fine. If you want to do it through a current frame rotation, that's fine. Okay, it does not matter. In this case, I can choose not to do X first. I can start with Y. We align Z0 first, right? I'm sorry, which axis? Yeah, we align Z0 first to Z. I can start by aligning Y or X first and do the other axis later. So these set of rotations or the order of rotations is not unique. You can come up with 2 other rotations that will do exactly the same thing, okay? I can start by doing a rotation instead of X. I can start a first rotation by Z. Then I can do Y or X or whatever, right? So the set of rotations is not unique. You can come up with any 2 rotations so long as these 3 axes eventually coincide with these 2, okay? The minimum that you need is 2. If you do something else, you probably will need, let's say, 3 or 4 rotations. Yes, sir.
So where D or 001?
I'm sorry?
Where D 001?
Why is D001? Because this is, if you look at the translation matrix, you have, this is,
Yeah, why G is 1?
because you translated along the z-axis. this is, you moved upwards along Z, right? You move this frame to this frame, right? So you're moving along the Z axis, so Z is 1. You're not translating along X and Y, okay?
Professor, is it Z or X?
This is Z. Thank you. All right. This is pretty similar. Let's try to move this frame here, okay? Let's try to do H1, 2 or 2, 1. Let's do 1, 2. So moving frame 1 to frame 2. Okay, let's try to move frame 1 to frame 2. All right, so frame 1 is and we want to go to frame 2, which is the following. Okay, first to move this frame here, what type of translation do I need? If I want to move this frame F2, if I want to move F1 to F2, because we are moving F1 to F2, what type of translation do I need?
You need to go to this.
Huh?
Minus
Minus root 2 about what axis?
Y.
No. Y is within the board. Don't think that this is parallel. This is not an extension. It's only within the board.
One unit in the x-axis and -1 on the z-axis.
Yeah, you can do that. Or you can do, what you can do is you can do one rotation first, which is I'll align X like this, then go up by root 2. Okay? You can align one axis with this line first, and then go up by root 2. Alternatively, you can bring, okay, so for example, if I want to go down this case, so what I'll do is this axis, I'll rotate X so that X moves like this. Once X aligns like this, then I can go down along X and come down. If I want to go up, I'll move Y along this or X along this, whatever axis you want to align, and move along that axis. At this point, Z2 and Y1 are perpendicular. This is coming out of the board, that is going within the board, so it's not along that line. Okay, if you don't want to do that, what you can do is you can drop it like this and then move in this direction. So let's say that our order of translation is like this. First we'll align the two, coincide the two origins. So this is what we'll do, 1 and 2, we'll move it like this. Okay, so this translation will be, translate, you're moving in the X direction, X by 1. What about this one? Z by?
-1.
By -1, because this is in the opposite direction. This is the positive direction of Z, right? So when you move in this direction, it's going to be the negative direction, so Z by -1. So for H1, 2, you'll have this as, first one is translate along X by 1. Number 2 will be translate along Z by -1. All right, now let's do the two rotations. Let's say that in this case we are moving from here to here, right? So we need to align one axis first. Let's try to align, okay, let's try to align Z. So Z is parallel, we want to bring it outside, right? So if I want to do this, this is my natural rotation, so I'll do it like this. So I'm rotating like this by 90, right? I'm rotating it like this. So when I do so, Y will become in line with the board. Okay? Z will come outside, Z1, and this will be X1. Okay? So this rotation is like this. It's in the positive direction of X, rotate X by 90, right? So this will be okay? So point your thumb towards the direction of the axis, and if I rotate, Z will come out. What is the next rotation that I need?
Along the z-axis.
Along the Z-axis by what? So this is Z, right?
Yes.
I want to,
Minus 90. No, plus 90.
huh?
Along the z-axis by
180?
180 will just flip Y on this side,
So it's 90.
right? Positive 90 or negative 90. I'm rotating it like this. So this is, Z is outside the board like this, right? So if I rotate, I want to move Y upwards. So I'll have to go in the positive direction of Y, okay? So when I move this, so it's like this. I'm moving it upwards, so 90.
So negative 90.
Why is it negative 90?
no, plus.
So when I do this, Y will be upwards, X will go like this, and this will be 0, okay? Which will be exactly like this. Okay? So when we multiply this, H12 will be equal to the product of all these. X will be